Good afternoon, everyone. My name is Philippe LECLERE, and I would like to discuss with you some of the results that we got recently in the framework of this BIOHARV meeting, and mostly the work done by Thanh Quang Nguyen, who is finishing his PhD together with Sophie and myself. As indicated in the title of this contribution, we would like to measure and estimate the piezoelectric properties at the nanoscale of those PLA-based electrospun nanofibers. Before that, I would like to remind you what we heard early during the talks, that the context of BIOHARV is to try to use piezoelectric polymer because of their environmental friendly, the cost-effective and efficient alternatives to the well-known ceramic piezoelectrics. We also heard from the previous talks that PLA could be presenting a potential interest in this field because of it's a cheap bio-based polymer, easy to process, and you can make either film or nanofibers out of that. And also, which is extremely important, it presents intense and spontaneous piezoelectricity without any pooling of the polymer. So indeed, what you see here on the PLA is presenting a very nice and interesting and promising piezoelectric constant compared to the other polymer. Before going to the scanning probe microscopy, which is a technique that we will use, I just would like to remind you what is the link between the charge generated by a device and the stress applied to this device, nanofibers or thin film. So, for instance, for a direct effect, there is a relationship between the charge, electric charge D, which is generated, for instance, in direction Y, and you are measuring the mechanical stress applied on that. On the other hand, what you have is the inverse effect, in which what you are doing is to apply an electric field and you are measuring the mechanical deformation of your sample. And those relationship comes from this matrix, which is actually a tensor, depending on the direction on which you apply a constraint, and you are measuring the effect of this constraint. So indeed, in most of the polymer that we will see and we saw before, we have the D33 or D31, which are the most tensile piezoelectric constant, but for PLA, it's more the shear piezoelectric constant that are involved, and that's why we have to measure the D14 or the D25. Just a reminder for the PLA, so we have this chemical structure of PLA here, and as mentioned before, if you want to get the polarization out of this material or this polymer chain, we have to apply a stress to or a shear strain to generate the polarization, corresponding actually to this matrix, this tensor with the D14 and D25 as mentioned before. Just in a nutshell, what the scanning probe microscopy is doing or is aiming at, actually what you have a small tip represented in green over there, scanning the sample, and to see and to get the information about the topography, what we are doing, we are shining the back of the cantilever with a laser diode, and the light is reflected to the quadrant photodetector. And by measuring the position of this laser, we can have an information about the topography of the sample. But on top of that, what we can do is also measuring some extra properties, as we will see in the next slides. So this is one way of doing scanning probe microscopy. There is another one. This one is to record the so-called force distance curve, in which you are sitting on a pixel and the scanner is moving up and down, and during this you are measuring the position of the reflected laser, the spot laser, and you are recording this force curve for each pixel of the picture. This force curve is describing the interaction between the tip and the sample. In Mons, we have the opportunity to have a lot of scanning probe microscopes, and we have a lot of modes to be able to measure different properties. We have this well-known methodology to measure the morphology of a sample, being polymer, fibers, and so on. And the most use is the well-known tapping mode. If you want to measure the electrical properties, there are a zoo of technique, but for this piezoelectric properties, we will of course discuss only a few of them. And for the mechanical properties, there is also an important set of different methodology modes to get the mechanical properties, including some modes able to provide the quantitative value of the parameter, providing the Young modulus, for instance, or these properties. So I will focus on these mode this afternoon, and I will just to summarize what is doing and what is possible to get out of these techniques. So for the mechanical properties, as we saw before, we are measuring the deflection versus time, and we are recording the force distance curve. And this is the movement of the piezo going from up to down and then coming out of the surface. And when you are recording those curve for each pixel of the image, and then by eliminating the time, if you know, of course, if you pre-calibrate your system, you know the deflection sensitivity, the Z sensitivity, it's possible to derive and to get this force curve, the deflection versus the position. Now, if you calculate out of that the indentation, and if you know the spring constant of your cantilever, and if you fit those data with a contact mechanic model, it's possible to generate what is known for people doing nano indentation, for instance, is the curve corresponding to the load versus the indentation. And you have this curve, and this curve you can fit with the mechanical model to get different properties. For instance, here the rigidity modulus. This is the DMT model in this case. So now, if you want to do that, because for one pixel of this image, it takes approximately 1 second, which means that if you want to generate a 512 by 512 pixel, you need almost 3 days to do so. So the idea is to work faster, and thanks to the peak force tapping, you can proceed to one force curve with a frequency of 1 or 2 kilohertz, which is 1,000 times or 2,000 times faster. And out of that, we can generate the force curve. And this is what we observe here. So we have this force curve, and in real time, it's possible to calculate, for instance, here, the rigidity modulus by the DMT as we saw before. We can measure, estimate the dissipation, the indentation, and the deformation. So when you are measuring and performing peak force tapping, what you have is actually 8 information corresponding to what you have measured. You have the adhesion, you have the modulus, the lock modulus, the dissipation, the stiffness, the deformation, and the indentation. Another mode which we will use also is the so-called intermodulation AFM. In this case, what you are sending to the cantilever to vibrate is 2 frequencies close to each other, and when the tip is interacting with the surface, you generate some side frequencies, some side bands corresponding to the intermodulation product. And when you have those spectra, actually, so the amplitude and the phase of all of these frequencies, it's possible to generate the evolution of the force in phase with the solicitation, or out of phase in quadrature with the solicitation. And these typical force, you can use them, you can analyze them to get, for instance, the viscoelastic properties. For the piezo response force microscopy, what we are doing, as I mentioned before, we will use the converse piezoelectric effect in this case. And what we are measuring actually is the deformation when you are applying a voltage to the tip, between the tip and the sample. And we can measure either the vertical PFM signal or the lateral PFM signal. The problem of this technique for the moment so far is it is working in contact mode. And you know that in contact mode, you can destroy sometimes your sample. I will come back later at the end of my presentation to see if we can provide some other technique to be less destructive on the sample. This is typically what we can record with the PFM technique on inorganic compound, and you can pour, you can write, and this is a very nice review from Rama Vasudevan from Oak Ridge National Lab, who characterize and measure different thin film, being PZT or BFO, and you can get those information thanks to PFM. Another example that we know, and we heard about that also today, is about the PVDF TRFE, and this is a recent paper proposed by Johan Hafner from Wien University, in which we have some kind of rise of this block of polymer, and you can see on this image that you have some lines corresponding actually to the amorphous and the crystalline phase of those grains or rise of the PVDF TRFE. This is a schematic of what we can expect when we have this kind of polymer. As we saw before, and because of the subject of this talk will be about PLLA, polylactic acid nanofibers, we saw that a paper from Sultana that in fact electrospun nanofiber can present some piezoelectric properties. This is the typical shape that we will see later with the hysteresis curve or this butterfly shape by applying a voltage, and you can measure the amplitude or the phase, and out of that it's possible to derive the piezoelectric constant. So it means that even if the PLLA is known to present some polarization if you are the shear force, it appears that for amorphous polylactic nanofibers, thanks to the extrusion, it's possible, the electrospinning, sorry, you can present the D33. So which means that with this kind of electrospun PLLA nanofiber, it's possible to measure those coefficients with the scanning probe microscopy as we saw before. So this is the setup used by Kyung, and this setup is actually located at UMET, and this is the way to electrospun the nanofibers. We have a high voltage, which is a syringe, and the collector, and by changing and adapting all the parameters, it's possible to generate a web of nanofiber as observed here in the optical microscope. So the polymer is ejected through a needle which is connected to a DC R voltage, and for instance here it was about 28 kilovolts and the distance was about 15 centimeters. So this is what we observe in tapping mode, which is just the mode, as I told you before, just to measure the topography of the sample. So this is the S-spun nanofiber, just one isolated nanofiber. This is the topography, this is the phase, and you can see that you can distinguish the fiber, which is softer, appears softer than the substrate, which was here a glass substrate, and we can measure the diameter of this fiber being about 250 nanometer. We heard that annealing is increasing the crystallinity, and the crystallinity is a key word for providing piezoelectric properties out of these PLA fibers, and this is the corresponding annealed PLA nanofiber, which is restrained, and we can see here now the nanofibers are about 170 nanometer, and it corresponds actually to the fact that upon annealing you can create some crystalline phase, while before it was more mesomorphous phases. So thanks to that, we increase the crystallinity locally, generating the observed piezoelectric properties when we annealed the PLLA nanofiber. So as I said before, thanks to the peak force tapping, it's possible to get the mechanical properties. This is another fiber which is larger. In this case, it's 340 nanometer, and this is what the mapping of the rigidity modulus. We have roughly a fiber which is about 2.2 gigapascal, while we have here the glass which is, as we know, about 60 gigapascal as a rigidity modulus. You can find all the details in the recent paper from Kyung about this work. So by collecting the mechanical properties with different diameter and different situation has spun or annealed, you have the evolution of the mechanical properties, which is important in this case, versus the diameter of the fibers. As we saw before, thanks to the intermodulation AFM, it's possible to go behind and to get more information about the mechanical properties. And since we are recording 42 different channels, the 42 different frequencies, the amplitude and the phase of these 42 frequencies ranging above and below the resonant frequency, it's possible to reconstruct the force curve, as I told you before. And this is typically what you observe on the PLLA. In red we have the S-spun, in blue we have the annealed, and in black this is the polystyrene. And the typical shape, I will not enter into the details here, but when you have this kind of force curve, it corresponds to the fact that the deformation is purely elastic. If you have viscoelastic properties, you should see some hysteresis either on the Fi curve or the Fq, the force in quadrature with the signal which is sent to the cantilever. So if there is no hysteresis, it means that with this PLA, it's not a viscous PLLA nanofibers, it's more elastic ones. Now it's time to move to the piezo force microscopy, and this is what we are using. This is the dual amplitude resonance tracking. In fact, I will not neither enter into the details, but the idea is to be able to measure the resonant frequency, and there is a shift of this resonant frequency, and the stiffness that we want to measure, mechanical properties, is proportional to the frequency shift, depending on the interaction that you have between the tip and the sample. And the quality factor of this resonance peak will tell you about the dissipation. So we have this situation, and one way to measure and to estimate and to track the frequency shift amplitude is to use this dual amplitude resonance tracking. In fact, we are applying two signals, and the idea is to nullify the difference between A1 and A2. Be sure that we have the frequency always in the middle of frequency 1 and frequency 2. This is a trick that we are using. Most of us are using to be sure to measure this frequency. Another important point before going to the data is the fact that if you want to generate those shape, amplitude, and phase that we saw before, we have different mode, either the continuous DC mode or the pulse DC mode. The problem with the continuous DC mode that you are generating and you are influenced by the electrostatic force, which is not that you want to measure. You want to measure the pure piezoelectric properties. So that's why it was introduced the fact that you are writing, you are polling the sample, you are writing something, and then you are measure with when the DC is off and the AC is on. So it means that you have different step, writing and reading, and instead of having this, which is not the actual value that you are expecting, because there are contribution of the electrostatic, it's better to have this kind of shape which corresponds to the pulse DC mode. So this is what we use, and this is, for instance, the evolution of the bias versus time, and you can see that with that we have different aid, and we are measuring always at this situation. And this is what you observe with S-spun nanofibers. So we have this butterfly shape and this hysteresis loop for the phase and the amplitude for the S-spun and for the annealed sample. So it's possible to measure out of this PLA nanofiber some piezoelectric properties. The problem now is to calibrate and to be sure that we are measuring correctly those PFM properties or piezoelectric properties. Some aspect now that we are continuing, and this is what Kyung is doing for the moment, is to make some electrospun nanofiber. The idea is to add some barium titanate into the fiber. He started to use a PVDF BTO because we know that PVDF is a well-known and with promising results with those nanofibers. So this is the SEM measure. You can see some aggregates of BTO along those fibers. But what Kyung did is to use PLLA These are a set of samples, and for the moment those samples are moving to Oak Ridge, and thanks to the work of Liam Collins, the idea is to use up-to-date technique, PFM technique, to be sure that we are measuring correctly the PFM signal, as we saw before, and also during the other talks. The S-spun or S-prepare, most of the time the samples are amorphous, and to increase the crystallinity, which is the key parameter, as we saw before, we have to anneal the sample, and these are the sets of samples that now are estimated and measured at Oak Ridge. So this is some SEM picture of those PLA BTO composite, and we can see that there are a lot of small grains corresponding to the BTO nanoparticles or particles. And with the this is the work done by Kyung as well. So this is what we have now with the tapping mode, and you see that from the mechanical properties, it's impossible to see a difference between the BTO and the polymer, because most probably the BTO is just embedded in this nanofiber, and the idea, because it's homogeneous here, and the idea is to get and to see if the incorporation of BTO nanoparticles into the fiber will increase or not the piezoelectric properties that we are aiming at measuring and use for devices. So as promised before, and I will finish with that, the idea, because in most of the technique that we use, PFM, we are in contact and the force is quite large. The idea is to combine the piezo, the piezo measurement with the peak force tapping, because in peak force tapping, what we are using, you can master the force at which you apply, the force that you apply to your sample. And during this time window, when the tip is in contact with the sample, you can start to play with the piezo itself, and you apply the, as we saw before, the AC and the DC, and we measure from the deflection curve or the lateral force curve, you can get the vertical lateral PFM as before. And on top of that, in the same experiment, because you are doing peak force QNM, you can have the topography, the adhesion, and also the rigidity modulus. And during this time, you can use the switching spectroscopy. So we have this shape of signal, and we are measuring, of course, when you are reading and not writing. And we can have different scheme to apply to this sample for each pixel, and this is another way to do that, which is called the nanopunt. This is a work done in collaboration with Brice Gauthier in Lyon. And this is the smartest way, that, to our opinion, to measure correctly and to be sure that what you are measuring is not too perturbated by the electrostatic contribution on your signal. So what we did, and this is now in collaboration with the people in Bordeaux, this is some PVDF nanofibers. You can see here a 5x5 micrometer scan size. This is the phase. If you zoom, you can see once again that those lines, and those lines are most probably, as we saw before, for the group, the work of Johan Hafner, is about the crystalline phase on the those fibers. And we started to make some PFM. You can see this is the amplitude in this case. You can see some blue lines, dark blue and light blue, most probably corresponding to the PFM signal out of these fibers. This is a work which is still under progress, but we now we would like to, instead of measuring the PFM signal on one point, we would like to map those properties. And when we have those maps, we can play with the voltage once we recorded those butterfly, and this is the data cube analysis, so we can see the behavior of this of these fibers depending on the voltage that you are applying to measure and to establish these butterfly shape. So another, and I will finish with that, it's about the nano DMA. So the idea is to get the mechanical properties, the viscoelectric properties locally by using exactly what happens in the macroscopic world with DMA, dynamical mechanical analysis. And the idea is to measure, when you are in contact with the sample, the mechanical properties. You have the preload, and you have the time to the polymer to relax, and you apply different frequency exactly as DMA is doing, and then out of that you can use the mechanical properties. But now we are not using the DMT, but the GKR, which is more appropriate for viscoelastic properties. What is still also ongoing for the moment is to apply a tension compression or bending on the sample just below the AFM tip, and to modify the sample and to see if you can generate, or by just flexing the flexibility of the sample, is we still able to measure some piezoelectric properties. We would like also to measure the influence of the temperature, and to see if, for instance, we have the Curie temperature of the system, and to see the evolution of the piezoelectric properties with the temperature, by modifying the temperature of the sample. And finally, but we mentioned that before, it's about the data cube analysis. So we have a map for each pixel. We can see exactly what are the properties. With that, I would like to thank you, and I will be happy to answer to your question. Thank you very much.